the culmination of our discussion, the summation of our discussion is something called the big O notation. The big O notation is a mechanism that allows us to track essentially what we call complexity. And complexity can come in two flavors. One is time and one is space. You see, the challenge that comes up is that, our natural reaction is how fast does this code run? And sometimes how fast this code run may be an important driver of what needs to be done, but it's not a good metric for comparing, because code is a function of how it's implemented, but also a function of which machine are you running it on. So you have a very powerful, 12th, 13th, 14th generation laptop with infinite memory and very fast SSDs. My code may actually run very, very fast on it. But is it efficient? We don't know. So big O notation is an implementation that focuses on, it's a concept that focuses on the complexity both in terms of time and space. And what we want to do is we want to think in terms of, as you increase the number of elements that you're working with. So in our case, that number is n. If you're calculating Fibonacci n, we're saying, okay, we're looking at the 10th Fibonacci, the 11th Fibonacci, the 100th Fibonacci, or the 1000th, or the millionth, or the billionth number. Similarly, if you're doing factorial, are we doing 10 factorial, 1000 factorial, 1 million factorial, or 1 billion factorial? If you're doing sum of all numbers till n, are we doing 10,000, 100,000, so on. So n is the number that we work with. And so far in this course, in the previous week, we looked at binary search. This week, we looked at Fibonacci prefix average. And we've spoken about, very, very briefly have we spoken about matrix multiplication, but we haven't actually touched upon matrix multiplication. How do you grade them? How do you rate them in terms of time complexity? You already have a sense because you've done some of the math, you've run some of the numbers. We haven't just introduced the terms. So the terms that we look at, for example, if you're looking at binary search, I'm going to come back to this a little later. But if you come back to the concept of big O notation, the first, the fastest, the cheapest in terms of time complexity is O of 1, which basically means constant time. It doesn't matter how big n is, n can go from 10 to 1 million. The amount of time it takes to get that work done, run that piece of code, is going to be constant, it's not going to change. Can you give me an instance of O1? O of 1? Can you think of an example, a variation, where it doesn't matter how big n is, but O would always be 1? The time complexity will be constant. Let's say I have an array, or I have a list, and that list may have, let's say, n items, and n can be as big as we want, but I'm referencing A0, or the first element in that list. What's going to be O1 for that piece of code? Constant time, right? You remember hash functions and hash tables? What would it take to look up a value in a hash table? Once you've done the calculation, once the hash table exists, if you remember when we did the search calculations last time, hash tables were much faster. Yeah? Okay, so this is the first one. Now then you come to, so I've got 5-6 items here, but I'm going to go through one. My next one is O of n right now. O of n means what? O of n means linear time. Linear times mean, if I run a for loop, the for loop is going to run how many times? From 1 to n. So it'll run n times. When we do, just by the way, when we do this analysis, when we do these calculations, we don't look at the best case. We don't even look at the average case. We're looking at the worst possible case. Right? So for example, if I'm looking at 1 to n, there may be instances where the algo or the code or the logic that I'm reviewing may terminate and finish early. There are tweaks that I can add that can make it go faster. But as long as the worst case is O of n, we will look at O of n. If you have 2 for loops, what do you get? You get n raised to the power 2. If you have 3, you get n raised to the power 3. If you have 4, you get n raised to the power 4, right? That is O of n squared. And then Fibonacci, the recursive implementation of Fibonacci that you saw was O raised to the power 2 raised to the power n. And this is what? This is exponential time. So this is quadratic time, this is linear time, this is constant time. Then we come to log n, right? What is log n? Do you think log n is faster, or do you think log n is slower than n, O of n, or n squared? If I were to ask you to rate, so if you ignore O of 1 for a second, right? If you ignore O of 1, look at n, n squared, 2 raised to the power n, n log n, which one of these do you think is fastest in terms of time complexity? Which one do you think is the one that you want to aspire for in terms of time complexity? Yeah, so log n is right, but now which log is it? Is it log of base 2 or log of base 10? Can you give me an example of something that we've done in this class so far, not just today but in prior classes also, which runs in log n? Yeah, it's log of base 2, larger the better, very good. Can you think of an instance or an example? No, that's not log n. That wasn't log n. You remember this? Binary search, iterative? So think about this for a second, right? How do you start? How does your logic work? You basically saying, I have a list, and on this list, this is the starting point, and this is the ending point, and then this is the midpoint, and then what do? So if I remember, so let's say this was 0, and this is 280,000. And we're looking for a given word in the Collins official Scrabble dictionary. What was the strategy? Our strategy was, okay, let's find the midpoint. And let's say the midpoint is at 140,000. And then what do? In binary search, we check if this is the answer and this is the answer, that's great. If this is not the answer, then what do? Then we check, okay, so for example, let's say I'm looking for the word axe. And this would be A and this would be Z, and let's say the midpoint comes at about K. So now, is axe less than K or is axe less than Z? And because axe lies between A and K, what do? I repeat this process here for 1 and K. So from 140,000, I reduce it again to how much? To 70,000. And then from 70, I reduce it to 35. And then from 35, I reduce it to what? I reduce it to 17,000. And then from 17, 8,500. Then 4,250. Then 2,125. And then I go back again. Let's say 1,100. Then 550. Then 275. Then 180. Then 90. Then 45, then 22, then 11, then 6, then 3, then 2, then 1. So in terms of number of steps it took me to find my answer in a list of 280,000 words, how many steps did I have? So 280 to 140 was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. My worst case is 19 steps. What do you think is log 2 of 280,000? Can you run that on a calculator and give me a heads up on what does that number look like? What do you think is the answer? What's log base 2 of 280,000? 18, exactly right. Actually 18.09. Do you see what we just done? So now rather than doing this by hand, if I said, okay, I have a list of 1,000,000 numbers, what's going to be the log base 2 of 1,000,000? How many steps is that? So about 20, right? So 2 more steps. So you can see that as you increase n, you took n you increase n by about 5 times. And how many steps did that add to your calculations? Did it add 5 steps? Did it add another 600,000 or 7,000 steps? No, it just added 2 more steps or 3 more steps in your calculation. And that is the power of log n. And this code, this algorithm that we have here does just that. This is the binary search iterative model, where you basically, the same logic that we've executed on that bar on the slide next to this, this is the logic that we work through. It essentially halves the list you're searching at every step. And it keeps on doing that till you find the item that you're looking for. O of 1 is constant time, O of n is linear time, O of n square is quadratic time, there's also cubic time. Then O of 2 raised to the power n, or c raised to the power n, is exponential. Then there is log n, and then there is n log n. So now there are certain basic simple rules that I want to emphasize, and one of the things that I want to look at is what I call relative time. Now, log n is the best in terms of time complexity. If you can O1, On is best, but O1 is generally very limited algorithms, very limited set of computations, restricted applications. But O of log n is great. If you could do n also works. So you can do n log n, you can do O log n, you can do other variations. What I want to show you is this plot, right? So this is a plot of On. So the orange line that you see here is On. The blue line is log n, and the gray line is n log n. Okay, make sense? I'm just establishing scale. So what you see here, so I'm looking at, if I take, what does this graph, what does this plot show? If I have n equals to 10, my input is 10, what is the amount of time it takes? And if my input is 10,000, what is the amount of time it takes, right? So if you see for O log n, doesn't even register on the scale. If you look at n log n, this is the number of seconds it takes, about 0.14 seconds for about 10,000, for n 10,000. And for On, which is linear time, are you clear about this graph? Do you understand how this graph represents? Because it's a multiplication, right? No, it's not to the power, it's n log n, right? So now if I move on to the next part, right? Next chart does what? It brings in n squared. So the yellow line now is O of n squared. And this is now to scale. So you remember here n log n was a horrible choice compared to log n, but that horrible choice at n equals to 10,000 was at how much? 0.14 seconds, about 140 milliseconds. But when we do n squared is now at about 100 seconds. Forget log n, even n log n doesn't register with respect to n squared. Do you get a sense of scale? Do you get a sense of how relative time is when it comes to complexity? I'm going to show you something. So this is a table, old slide from one of the many lectures that I'd looked at earlier. This slide shows you the amount of time it takes when you're running it on a processor or a machine where you get about 1 million instructions per second. So basically a 1 MIPS machine, 1 million instructions per second, right? So on a 1 MIP machine, if you have n equals to 10 and you run something for log n, this is the amount of time it takes. If you're running n squared, this is the amount of time it takes. This is what we've plotted, right? This is what we plotted. So if you do 10,000, it's still about 1.7 minutes. It's only when you run it for 100,000 n that you find out that n squared is a challenge, is a problem. In most instances, when we do work, if you look at your ITP assignments, you look at other programming assignments, you'll do data structure assignments, do you think you'll actually have the time or the capacity, or your instructors would ask you to test your code for, let's say, a value of n equals to 1000? No. So if you're running it, let's say, for a loop that runs till 100, do you think you'll notice that your machine is running it in 0.1 second or 100 milliseconds? You won't. So when we write codes, especially at the undergrad level, especially in our initial years, it is very easy to pick up bad habits because we don't notice that our code is running slow. And the reason why we don't notice our code is running slow is because there is no need for us to test it at, let's say, 1,000,000 iterations or at 1 billion values. If you do n squared for 1 billion n, it'll take you about 320 centuries to knock it out on a machine that runs on 1 MIPS. It'll still be, before you blink your eye, it'll be done if you're on log n. That is relative time. Now, the context perspective, what is important is you also have to understand what is the processing power at your disposal. So if I go back to, let's say, here, this is, I've not gone back to the time. Yes, you can, Shahir. And the reason why you can compute it faster is because if you go back to, let's say, Intel Pentium all the way back to, let's say, prehistoric times, fossilized times, which is the times that I come from, an Intel Pentium machine all the way back in, let's say, 2003, 2004, 2005 would do about 188 MIPS. It's about 200 times faster than the benchmark that we looked at. And then a Pentium 3 machine was doing about 2000 MIPS at 600 megahertz. Can you guess where we are now? So a third generation i7 is about 176,000 MIPS. A third generation, a 6-core third generation i7 is 176,000 MIPS. And i9, a 9th generation. I think right now we're on the 13th generation. I think the most recent one series that we've seen with i9s is maybe 12,000 or 13,000 something. So 12 to 13 generation. But even then, a 9th generation 8-core Intel machine was about 4,000 MIPS. 400,000 MIPS. So with this powerful a machine and with a smaller data set, you will never find out that your code is inefficient. When will you find out when your code is inefficient? When you're running it in millions of iterations, or when you're running it on a machine which is, doing other things also on the side. That is when you'll know that your code is not efficient. Okay, now one more point. There is a notation, and there's a notation convention that I want to emphasize. I want you to remember this because this is really key. When we speak about notations, right? If I say I'm running at, so if I'm analyzing a line of code or a sequence or an algorithm or a function, and I say, when I add up all the calculations add up to 3n plus 5n plus 3n squared. What is the time complexity of this effort, of this growth of work? You should only focus on the highest power, not even the coefficient, All of this is relevant. This is O of n squared. And then similarly, if I say 6n plus 5n plus 4n squared plus 3n cubed, this is my assessment of the work required in this algorithm. In this specific instance, what is the complexity? O(n) cubed. Very good. So this is going to be n cubed. Now, if I have n log n plus log n plus n cube. What's the complexity? N cube. So the highest level of complexity is what you are seeking. You're not seeking, that's what you want to zero down to. And your objective is to reduce this. Okay, your objective is to reduce this. Your objective is not to focus on, let's say, so if you're at log n, that's great, that's fantastic. But if you're not at log n, then focus on this part.